general relativity step by step. I'm going to talk about curvature. Curvature of a space in the way that the surface of a sphere, there's your north pole and there's your south pole, is curved. And you'll remember I talked about the fact that you can't parallel transport a vector around a sphere without it changing. So I'm going to quantify that and use tensor calculus to do so. So what I want is to imagine a small transport vector A and then another one B, and I'm going to take it backwards along minus A, I guess, and down on minus B here. So these are little vectors here. And I'm going to transport a vector which I'm going to write in a different colour. I'm going to write it in red if I can find my thing. Here it is. So I'm going to transport it around like this, and it might be changing in some way like that, and then it'll change. Actually, it won't change that much at the corner, because by construction the corner is a nice smooth part of your manifold, so it'll change around like this, might change in all sorts of funny directions, and then it comes back here, and lo and behold, it's changed from that where it started to this when it's come around this picture here. I'm actually going to write it in a slightly different way. That's what you see in the literature, but I'm going to talk about delta A is a small vector, and the components of it I'm going to write like that, and that's the components of the small vector. And we've also got delta B, J, I guess. So what I want to do is I'm going to talk about the change in a vector V with components, let's say I, and what I want this is what I want. It's going to be something that's proportional to the vector Vi where it started, which is not necessarily small, but the change is small. It's going to be proportional to A, let's say J, and B, K. I'm writing this all backwards. Times something. And that thing will be contracted on K and J and I. Different people write it in different ways. It's enough to drive me crazy. Let me just say this and then, okay, and it's going to times a vector V, which is IJKL, and it's going to this thing. No, that thing is. You see the problem? The problem is I've casually written an I down here, which I want to be a summed index, but this one is a free index. So let me write that out again. Delta V and I is going to be a free index equals something which I'll reveal to thing, which I'm going to reveal to be the Riemann curvature tensor. So that's got an I there, but it's going to be contracted with respect to all sorts of other things. So I've got my V. No, I'll do the deltas first. I'll do the delta A, and I'll put it further over there. Delta A times J, delta B times K, and I'm going to contract on the J and the K. And what else have I got left? I've got my original vector V, which has got contravariant component L, which I'm going to put down there as well. So this is what I want. And of course, rather than this thing, I'm going to call it R, IJKL, and this thing here is by definition the Riemann curvature tensor. Now if we have parallel transport, so parallel transport implies that the Riemann curvature tensor equals 0. But of course it's not 0 for the surface of the sphere, as I was saying earlier. Care is needed here because lots of people define it in lots of different ways, and it is very, very easy to pick up an incorrect definition. Some people lower one of the upper indices there. There's different sign conventions. I guess you can't get around it. Whichever way you do it, somebody else will say my way's better. Anyway, so that's the basic idea. So it amounts to basically taking a second derivative or a derivative in two different orders. So I'm gonna show you how that works. What we want to do is to have a vector v, and again, different people do it in different ways. So I'm just going to follow. I'm going to follow the majority. We're going to talk about. Yeah, I'm going to follow the majority here. I want to talk about a vector v with contravariant components I. Rather than just differentiating it, I'm going to take covariant differentiation with respect to j and then k. So what do I, and I'm going to subtract vi semicolon kj. So I'm swapping the order of these two differentiations here. So we've got vi semicolon j semicolon k minus vi semicolon k semicolon j. Yeah. And that is going to equal the Riemann curvature tensor contracted with one of these guys, ijkl. There's going to be an L. Which way round is it? It's going to be L on the first index there. There's going to be an I up there, and I've got a J and a K. But be warned. So let me just make clear what this thing is here. So I'm going to use my colouring trick here. So I've got a free index I, which is here and here, which matches this one here, I. J and K I'm going to leave, but the summation is over index L. And the reason I paused, the reason I was getting myself confused, I'll do the summations in blue. The reason I was getting confused is that there's no L, and that one should be a J there. I guess I'll replace that with a black there. There's no reason for it to be that way around. I could have contracted on the third covariant index, but I'm trying to be consistent here. Different people do it different ways, and of course there's a sign error here. So what I'm going to do is to evaluate this beast and see what happens. It's all about failure of parallel transport of a vector with contravariant components. It's not a failure, it's just that when you follow a path, your vector has changed. Your vector has changed, and we need to keep track of that somehow. And this is the right way to do it. Whew. This is quite complicated, and there is quite a lot going on. So I'm going to do it one step at a time. I might change from I, J, K to A and B and C and D and E and possibly an F as well. Simply because, well, I think A's and B's look nicer than I's and J's. And also, I don't like this. I don't like having a semicolon and a J, because quite frankly, my semicolons look rather like J's. So I don't like J's. I'd much rather have a semicolon A. Okay, well, I'm going to define all these, and I'm going to remind ourselves what the covariant differentiation operator is, and what a covariant derivative is. And I'm going to do that in the next screencast. So I'm going to stop there before I cock it up, basically. I'm going to stop there and define this Riemann curvature tensor. Stop.